Splunk Observability Cloud is an observability platform that provides full fidelity monitoring and troubleshooting across infrastructure, applications, and user interfaces in real time at any scale and across any stack. It provides complete business visibility. This means you can monitor your critical business processes, things like sales, orders, and customer abandonment, all in one place. You'll be able to see every user transaction, eliminating blind spots, and you'll gain comprehensive visibility across all your applications and infrastructure, whether they're commercial off-the-shelf, homegrown, monoliths, or deployed as microservices. Next, Splunk Observability Cloud enables earlier detection and faster investigation. You can search and analyze both unstructured and structured data at petabyte scale, leveraging dynamically updated out-of-the-box visualizations. Our platform provides real-time detection and guided root cause analysis, and it uses event correlation to reduce alert noise. Plus, you can easily instrument, tag, and analyze high cardinality metrics. And finally, Splunk Observability Cloud gives you better control. It's OpenTelemetry native, so you can avoid vendor lock-in. You can reduce toil by instrumenting once as you build new applications, and our enterprise controls enable self-service observability for your teams. I cover a lot in this video, but I've included chapter markers that you can use to navigate directly to the sections that you're most interested in. Here's an overview of the chapters. First, I'll provide a brief overview of Splunk Observability Cloud's key capabilities. I'll then introduce you to infrastructure monitoring, and we'll take a look at Kubernetes Navigators. From there, we'll look at detectors, alerts, and SLOs. We'll then take a look at metrics, traces, and the service map in APM. To troubleshoot high error rates for our service in APM, we'll review logs in Log Observer, as well as profiling data using AlwaysOn Profiling. But to fully understand what the users of our service are experiencing, we'll dive into real user monitoring, and then explore more proactive monitoring using Splunk Synthetics. I'll show you how to get data into Splunk Observability Cloud using our guided setup wizard. We'll briefly discuss how you can control the volume of data being ingested to Splunk Observability Cloud using metrics pipeline management. We'll finally wrap up with a brief demonstration of how you can use the AI assistant in Splunk Observability Cloud to troubleshoot your services, and then end with a brief recap and conclusion. With that, let's get started. Before beginning the demonstration, I'll give you a quick overview of Splunk Observability Cloud's key capabilities. If you just want to see them in action, you can use the chapter markers below to skip ahead. Infrastructure monitoring provides real-time streaming metrics, monitoring from on-prem to multi-cloud, automatic service discovery, and analytics-driven alerting for faster problem isolation. Splunk APM provides full transaction analysis of every trace, in context with every metric time series, and log event data to scope and isolate issues faster with more context. And Splunk Real User Monitoring captures full user sessions from single and multi-page apps, as well as iOS, Android, and hybrid apps. Splunk Synthetic Monitoring proactively monitors performance and ensures exceptional customer experience through URL, API, and service performance alerts, with more than 50 public locations to simulate performance of users globally. Log Observer Connect centralizes data management by seamlessly connecting application and infrastructure logs from Splunk Enterprise or Splunk Cloud to Splunk Observability Cloud, enabling in-context troubleshooting and faster root cause analysis. Let's get started with our demonstration and explore these key capabilities as well as some additional features. So this is the homepage of Splunk Observability Cloud. From here, if I'm a member of a team, I can access the team dashboard by selecting this tab here. And on the team homepage, I can see services that are associated with the team, as well as various dashboards that are also associated with this team and its services. If there's any active alerts for the services that my team is linked to, those will show up in this active alerts table. The first capability that I want to demonstrate is infrastructure monitoring. To access it, I'll just select infrastructure on the left-hand side menu. From the infrastructure homepage, I can browse various types of resources, like resources from cloud providers such as AWS and Google Cloud Platform. We can also monitor other types of infrastructure like containerized environments. And what I'd like to show you are these Kubernetes navigators. I'll open the Kubernetes clusters navigator. The navigators are like dashboards, but they provide some additional features in addition to just charts. For instance, in this table, I can see a list of Kubernetes clusters. And if I keep scrolling down, I can see aggregated metrics for those clusters. And I can also view these clusters as a heat map. The heat map can help me quickly understand the health and status of a particular cluster. In this heat map, we're currently coloring each cluster by the number of containers that that cluster has. If I want to drill down into a specific cluster, I can just select the cluster from the heat map. Now I'm on the cluster navigator, which gives me a cluster level hierarchy map as well as cluster level metrics. I can also see the specific workloads that are running in the cluster and their status. I'll expand the hierarchy map. And this is a single node cluster, which we can see if I hover over this outer black line here. Inside of the node, you can see these green squares, and these are the pods that are running in the cluster. And I can click on any one of these pods to be taken to a pod level navigator. So from here, I can see pod level metrics, as well as a hierarchy map. And in the hierarchy map, you can see how many containers are in the pod. If I select the K8s Containers tab, I can get container metrics as well. There's also the K8s Analyzer, which will essentially identify potential patterns that could be causing problems in your cluster. The analyzer helps you troubleshoot Kubernetes problems at scale by highlighting Kubernetes instances that are in a bad state, such as nodes that are not ready. And it produces theories about what those instances might have in common, like all of the instances are running the same workload, or all the instances are located in the same AWS region. Now from this filtered view, we can see that there's 0 alerts and 0 active detectors. But I'm going to navigate up to the cluster level again. And at the cluster level, we can see that there's multiple alerts and there's also 1 active detector. So I'm going to select the alerts. And there's multiple major alerts for this cluster. And I'm going to select the first one here. So this first alert is called K8s container restarted count is greater than 0. And if I hover over this lightning bolt here that says auto, this says AutoDetect Detector. And what this means is that this detector was not manually configured by someone. This is a detector that comes out of the box with Splunk Observability. And there's multiple AutoDetect detectors specifically for Kubernetes environments, as well as AutoDetect detectors for environments like AWS and Google Cloud Platform. For this specific alert, the container restart value was 3, and we can see in the detail view when those container restarts actually occurred. If I scroll down, you can see a more detailed message of the alert, including the signal details. If I want to, I can navigate directly into infrastructure monitoring filtered on the containers that are included in the signal details, or I can troubleshoot in APM the services that are associated with these containers. These data links will take me to the detectors and alerts page, so I'm going to select one. And the data link that I selected was filtering based on the cluster name. So now I'm in the detectors and SLOs page, and from here, if I scroll down, I can see alerts, active alerts, and all of these active alerts are currently filtered on the cluster that we were just looking at. And if I want to view or create new detectors, I can just select the detectors tab here. If I type in the search bar, I can filter on the name of the detector. And if I type in K8s, we can see all of the AutoDetect detectors that are associated with Kubernetes environments. In addition to detectors, you can also perform service level monitoring using service level objectives. An SLO defines a target for a service level indicator and a compliance period over which that target must be met. And once you've defined an SLO, you'll be able to see your error budget as well as your burn rate. Now that we've seen infrastructure monitoring and detectors, let's take a look at APM. And once you've selected a target environment, you can view metrics associated with that environment. I can also view business workflows. A business workflow is a set of correlated traces that track a complete user transaction end to end. An example would be the checkout workflow, where a call to the web front end passes through the cart service, the payment gateway, inventory service, order service, and confirmation email service. Splunk rolls those traces into one workflow so you can view total latency, error rate, and throughput for the entire checkout journey at a glance. And those workflows should map to key business metrics. One of the key features of APM is the service map, and I can access a service map by selecting this service map card here. This allows me to easily visualize the interactions and how data is flowing between services in my environment. Each node in the graph is a specific service, and services are connected by these directed edges. And if a service is producing any errors, you'll see a red circle inside of the node. And depending on the error rate, that circle will be smaller or larger. So for instance, you can see the payment service has quite a few errors. And that's also indicated on the right-hand side metrics. If we look at top error sources, you can see that the payment service is at the top. If I scroll down, there's a feature called Database Query Performance. And if I open this up, I can analyze the database query performance for databases that exist in this environment. So for this MySQL database, I can view top queries by total time or the 90th percentile latency or by the number of requests. And on the right-hand side, I get even more charts and metrics. Navigating back to the service map, there's one thing that I want to call out. And if you look at the nodes of the service map, you'll notice that the MySQL database, for instance, is an empty node with like a dotted outline. And this means it is an inferred database, or if it's circular, it's an inferred service, meaning the service or the database isn't instrumented itself, but it's inferred from the requests that an instrumented service are making to that inferred database or that inferred service. Let's drill down into a specific service, and I'm going to select the payment service since it has errors. And when I select the payment service, it pulls up metrics on the right-hand side here. And if I select payment service here, it will take me to the service-oriented service map. So now I'm in the overview page of the payment service in the online boutique environment. And on this page, I can see service level metrics as well as a service map. If I look at the service errors chart, you can see that there's a number of errors, but also alerts that were triggered from those errors. And this chart is dynamic, so I can select any data point in the chart and it will bring up related traces that are associated with that data point. So I'll open up the first trace on the list that shows up here with an error. And if we click on a trace, then we can see the trace waterfall that includes all of the spans within that trace. In this particular span, the charge endpoint was calling the third-party payment service Buttercup Payments API. And this is an inferred service as noted by this small circle here. On the right-hand side, I can see additional metadata about the span, including the status code of the request. But I might want to look at the logs of the payment service and specifically the log entries that are associated with this particular trace. And to do that, I can utilize what's called related content that shows up in these bottom windows here. So if you're in APM or infrastructure monitoring or log observer, and you have selected an entity like a Kubernetes node or a pod, or you're looking at a specific log entry, you'll see related content show up at the bottom of the screen here. And this is basically automatic correlation between metrics, logs, and traces that you do not have to manually set up. So if I select the infrastructure related content window, I can go directly to infrastructure monitoring for K8s containers associated with the payment service. Or if I select the logs related content window, I can navigate to log entries specifically for this trace. And so I'll select this related log. And this takes me directly to Log Observer, filtered on the trace ID that we were just looking at. Now there's multiple log entries here, and not all of them are error logs. So what I could do is add a filter and select a field, and I'm going to select the severity field, and we'll filter on error log entries. And now we're specifically filtered down to the error log entries, and I can select a specific error log entry. And under the message, we can see that we failed payment processing through the Buttercup Payments API, and it's because of an invalid API token. And in this log entry, we can see the value of the token that's being used, and it appears that we accidentally used a token that was meant for the test environment and not the production environment of the payment service. The other thing that I notice in this log entry is the version value, and this is version 350.10 of the payment service. Another feature that we can use to troubleshoot our services is Tag Spotlight. I'd be curious to know if this is the only version that is utilizing this test token, or if all versions of the payment service are using the test token. If all versions of the payment service are using this test token, then we would expect to see errors in those versions of the payment service as well. So I'm going to navigate back to the payment service in APM. And I'll select the payment service. And then I'll scroll down, and I'm going to select Tag Spotlight. Let's scroll down and take a look at some of the tags in Tag Spotlight for the payment service. So if we're encountering errors in the payment service, Tag Spotlight will help us identify errors by tag. For instance, if I look at the tenant level card, there might be tenant levels like bronze that have more errors than higher tier tenant levels. And for the version tag, there's two versions of the payment service, 350.9 and 350.10. Now 350.10 was listed in the error log entry, and you'll notice here that we can see the number of requests and the number of errors that are associated with version 350.10. And the error rate and the 90th percentile latency is much higher than version 350.9. In fact, it looks like the error rate for version 350.10 is 100%. So this gives me a pretty good indication that the latest version of the payment service pushed the test environment token instead of using the production token for the Buttercup API payment service. And from here, we could decide to roll back that version or fix forward and update the token in a new patch. Now, in this particular scenario, the errors that were occurring were caused by a misconfiguration of our application. But what if we were receiving errors related to the performance of our application? How could we identify performance bottlenecks in a production environment? It's a challenging problem, but something that Splunk AlwaysOn Profiling is built for. AlwaysOn Profiling continuously collects stack traces so that you can discover which lines of your code are slowing down or crashing your systems. To access profiling data, I'm going to navigate back to APM. I currently have the online boutique environment selected, and from the home page, I'm going to scroll down on the right-hand side, and I'm going to select this AlwaysOn Profiling card. When I select the card, I can see a list of services that currently have profiling enabled, which includes the ad service and the cart service. I'm going to select the ad service. On the code profiling tab, you can see the stack frame table on the left-hand side, and each row represents a single method or function that's captured in production. And we also get the file name as well as the specific line within that file that this function or method is associated with. And then we can see how much CPU time that function consumed, as well as the number of times that it was invoked. And when I select a row, that row will be highlighted in the flame graph on the right-hand side. The flame graph allows you to visualize how much CPU time each stack frame consumed across multiple stack traces. Not only can we identify lines of code that consumed a lot of CPU time, but we can also review memory allocation data under the Memory Profiling tab. If the data is available, you can see heap memory, application activity, and garbage collection activity over time. And then similar to the CPU profiling, we can review a table of stack frames that show how much memory was allocated to a particular function or method. And clicking on any row spotlights that stack frame in the flame graph on the right. Now, in your typical troubleshooting workflow, you might not navigate to code profiling or memory profiling in the way that I just showed. The more likely scenario is that you would navigate into code profiling or memory profiling through an error trace. So I'll navigate to the Traces tab. And on the Traces tab, I can see traces with errors as well as long duration traces, and I'll select the top one here. When I'm viewing a trace and AlwaysOn Profiling is enabled, in each trace span, I'll be able to see how many stack traces are associated with that span. So in this span, there are 32 call stacks, and if I select the span, I'll get the span details on the right-hand side menu, and I can access the profiling data by selecting either the CPU stack traces or the memory stack traces. And if I want to see that stack frame table that we were looking at earlier, I would simply select the span link here. When we're looking at profiling data or metrics, traces, and logs, those give us an indication whether our service is experiencing a performance degradation. But if we want to know what our customers are actually seeing and what our customers are experiencing when they're accessing our application, we need to utilize real user monitoring and synthetics monitoring. So I'll navigate to the RUM overview dashboard. You can use RUM to determine if front-end, network, or browser errors are impacting your customer's experience. Let's look at one example customer transaction. I'm going to search for the user session using the search here. Now we're looking at a single real user session. And at the bottom, I get a waterfall of page views and key user experience metrics. And I can see more details of each of these spans by selecting this arrow. An important thing to notice here is the correlation to traces directly linked into APM for this user session. So if I want to, I can navigate directly to the trace ID associated with this user session in APM. And we even get a replay button which plays a lightweight film strip of the user's page transitions. So in one view, I can understand who the user is, where they were in my application, web vital timings, and the presence of any JavaScript or network errors, all linked to traces in APM. Now let's take a look at what else you can learn in RUM. The RUM dashboard can be filtered by environments, applications within an environment, as well as the source of a user session. And for a specific application, we can see things like page views and JavaScript errors over time, as well as network requests and errors over time. And if I scroll to the right, we get a table of the web vitals for our application. If I were to collapse this app, then I can see those same metrics, but at a glance, and it just makes it easier to digest the data if I had multiple applications listed in this environment. If I want to drill down into a particular application, I can just select the application here. The first tab in the application overview dashboard includes user experience metrics. So I can see things like page views or route changes with the top 5 endpoints. And then on the bottom, we can see core web vitals over time broken down by endpoint. And then switching from overall user experience to front-end health, we can focus on client-side code quality and responsiveness. The back-end health dashboard allows you to separate front-end code issues from back-end API issues or even network problems. Custom events are really important because they allow you to model your core business workflows and user journeys and determine the health and performance of them with real user sessions. If there's a specific custom event or endpoint that I want to see user sessions for, I can simply select it here under the chart. And then if I want to see user sessions associated with this custom event, I can select the User Sessions tab. And this shows me a table of user sessions that I can drill down further into. Real user monitoring is important to understand how your customers are using and navigating your application, but it is inherently reactive monitoring. And to perform proactive monitoring of our critical user journeys from locations around the world, we need to use synthetics. Let's navigate to the Splunk Synthetics dashboard. Synthetics monitoring allows us to simulate critical user journeys 24 hours a day, 7 days a week. From the home page, I can review a table of existing synthetic tests, and then I can select a test to see more details. If I scroll down to the availability chart, each one of these dots is a specific test run. You can see the unsuccessful runs on the bottom with a red X over them. And if I want to see the details of a specific test run, I can select it here. This is a single execution of the synthetic test. Across the top, you can see a film strip of screenshots taken every second. The table below the film strip is a full network waterfall. And similar to the real user monitoring user sessions, we have a direct link into APM. And on the right hand, you get this metrics panel, which includes key performance timings and resource metrics. And similar to the user sessions in RUM, you can even view a replay of this test. With synthetics monitoring, you can create browser tests, API tests, as well as uptime tests. So far, we've toured the outputs of Splunk Observability Cloud, which include real user sessions, synthetic tests, traces, logs, metrics. But how do you get telemetry data in Splunk Observability Cloud? Let's navigate to the data management page. This page provides a catalog of over 200 integrations from AWS to Kubernetes. If I want to see available integrations, I can select this tab. Remember that Splunk is OpenTelemetry native and offers a fully supported Splunk distribution of the OpenTelemetry Collector. And we also provide a setup wizard that helps you easily deploy the OpenTelemetry Collector to various environments. And if your applications are running in Kubernetes, one of the easiest ways to get data into Splunk Observability Cloud is by using our setup wizard to deploy the Splunk OpenTelemetry Collector to your Kubernetes clusters. To do that, I can scroll down and select Deploy the Splunk OpenTelemetry Collector. I'll select Next, and then I'll select the platform that I want to deploy it on. and I'll select Kubernetes. I'll leave gateway set to no, and then I can add an environment name as well as a cluster name. And if the cluster is running on top of a cloud provider, I can specify the provider in this dropdown. I can also use this dropdown to specify the distribution of Kubernetes that I'm using. So if I'm using a managed Kubernetes service like EKS, I could select that here. I can also specify if I want to collect logs. And if I do that, I would want to make sure that I've already configured a Splunk platform HTTP event collector endpoint, as well as the HEC token. The OpenTelemetry Collector will push application and Kubernetes logs to the Splunk platform HEC endpoint, and then those logs will be made available through Log Observer Connect in Splunk Observability Cloud. I'm going to deselect log collection. And I can also enable this feature called Auto Discovery. And if I enable this, the OpenTelemetry Collector will be able to identify supported third-party applications like Nginx or Redis running in my Kubernetes environment. And it will also perform zero-code instrumentation on supported language runtimes. And directly below that, you can specify which language runtimes would be enabled for zero-code instrumentation. And we can use this dropdown to enable or disable AlwaysOn Profiling. And then you would want to specify the Splunk Observability Cloud access token, which would allow you to authenticate to Splunk Observability Cloud. On the next page, the setup wizard gives you the exact commands to run on your Kubernetes cluster to deploy the Splunk OTel collector and start sending data to Splunk Observability Cloud. Splunk provides a Helm chart to deploy the Splunk OTel collector. So once you've added the Helm repository, you can run Helm install to deploy the Splunk OTel collector to your Kubernetes cluster. So you can see all of the data that we provided in the previous pages is passed into the Helm install command. And once you run that command and the OTel collector is deployed to your cluster, it will immediately start sending data to Splunk Observability Cloud. So that's one of the easiest ways to get data into Splunk Observability Cloud if you're running in a Kubernetes environment. It's worth mentioning that although you can get your data into Splunk Observability Cloud using one of these setup wizards, you might not want all of your data in Splunk Observability Cloud. And that's why as an administrator, you can control the volume of data that is being ingested in Splunk Observability Cloud using metrics pipeline management. For each metric that you send to Splunk Observability Cloud, you can use metrics pipeline management to help you configure how to ingest, keep, and manage the metrics data volume and cardinality. But even if you've gone through the process of filtering data, there's still a lot of telemetry data that you're going to be pushing to Splunk Observability Cloud. And it's challenging to turn that data into actionable insights quickly, especially when you're having like a production outage. So to help you speed up your troubleshooting process, Splunk developed the AI Assistant. You can activate the AI Assistant by navigating up here to the top right and selecting this icon. And then you can have a conversation with the assistant about metrics, logs, and traces in your environment. You can chat with the AI assistant using natural language to cut through complexity and get to answers faster. To conclude, let's do a quick recap of what was covered. We explored infrastructure monitoring and the Kubernetes Navigators, watching node and pod health update in real time. We also got to see alerts associated with our services and infrastructure using detectors and SLOs. We then analyzed traces and APM and looked at profiling data using AlwaysOn Profiling. From traces, we could navigate directly into Log Observer, where we could see related log entries for a given trace. We then flipped to real user monitoring dashboards to see core web vitals, JavaScript errors, and individual user journeys, verifying how backend latency actually felt to customers. But to stay ahead of users, we also looked at more proactive synthetic monitoring. This allows us to run automated synthetic tests all day, every day. And thanks to the setup wizards and data management, a single Helm command can deploy the Splunk OTel collector to a Kubernetes cluster and immediately start streaming metrics, traces, and logs. We can control the fire hose of telemetry data using metrics pipeline management, filtering noise and aggregating high cardinality data. And finally, we ask the AI assistant natural language queries, turning mountains of telemetry data into insight. Splunk Observability Cloud gives you end-to-end visibility, open standards data collection, intelligent alerting, and AI-powered troubleshooting in one unified platform. I hope you enjoyed this video, and if you did, we'd love to hear your feedback. And if you're interested in trying Splunk Observability Cloud yourself, you can navigate to this link to claim your free 14-day trial. Thanks for watching.